Hey folks, welcome back. Hopefully you had a good couple days off. Hopefully you're a little bit rested, recharged, all that good stuff. We're gonna start up Unit 4 today. I don't have a calendar here at my house, so I got to get into the building and see kind of what we got going forward for days, as far as test days and quiz days are concerned for us. Okay. So those are all kind of to be determined right now. Okay. So um, today what we're going to do is we're going to talk through something old to know, something new, and then we're also going to see, just some interaction forces and tension. We'll save Atwood forces for you until tomorrow when we have a little bit more time. Just going to try and be quick with these so that you get some introductory information here. All right. Stuff to remember from Unit 3. Make sure you remember how to do mass and weight. Mass, the amount of matter. Weight is the force of gravity. Adding one-dimensional forces or one-direction forces to determine fun. So if we got a force acting that way, force acting that way, remember those are going to subtract. If both forces are acting the same way, those are going to add. Finding fun given an acceleration or a mass. Finding fun and acceleration given multiple forces and multiple masses. So there it's just using fun equals ma and being able to run through the different variations of that. Distance versus time and velocity versus time graphs are still going to be kicking around a little bit for us. All right. What's new in chapter 4 or unit 4? Sorry. Tension in ropes, strings, cables, wires, etc., like that. Fun equal ma when two things are pushing on each other. Air drag, terminal velocity, and then this concept of momentum, which we talked a little bit about earlier, but we're going to go ahead and work through a little bit more later on. All right. Tension is a force. It's a stretching force. So when we start to see this concept of tension, and again, you've probably all had, a tensionary force, a string. Like if you're tying your shoes, that gets tight. If you've got a sweatshirt, well, my string is gone in my sweatshirt. Sorry. Pair of shorts you're tying. If you tubing behind a boat or something like that, or up at Buck Hill on the snowboard side or the kind of ski racing side, all those ropes are going to have tension in them, meaning there's going to be a stretching force, right? Um, when we look at this now, we can actually calculate this as well. So if we have a 10-kilogram object hangs from your hand by a string, how much does it weigh? So if we had just a 10-kilogram object, right? And we just held on to it with a string that was just down below it. We would take 10 times negative 9.8. So its weight would be negative 98. Now remember, weight is a force of gravity, right? Mass is just how much matter it has. That would be a 10-kilogram mass for it. Its weight is going to be negative 98 again because what direction is gravity going to pull on this thing? Remember, downward. Directionality now with tension becomes pretty crucial for us. So just be aware of that. Okay? So when we have tension, what we're going to see is that an unbalanced force in any system causes acceleration. Right? That was Newton's second law. So if we see that concept of an unbalanced force, a push or a pull, right? If you start to slow down, guess what? You have to apply force, right? So if you squeeze that brake handle on the bike, you're going to squeeze the two pads together onto the actual wheel of the bike. That's going to create a force. That force is going to cause negative acceleration or deceleration, right? If you push down on that bike pedal, right? You push real hard on that pedal, that gear, that chain is all going to start to rotate for you. It's going to allow that force to be redirected, and your bike's going to speed up, right? So in this, the unbalanced force is the difference between the tension and the weight. So when we look at this, that's a formula we want to have. F of t equals ma minus mg. Ma, that is the force. That is our unbalanced force that we have there, right? The mg, that is just our weight of the object. Now, what I want you to think about with this tensionary force is, and again, I'm not a big fisherman, all right? I think I've caught, I've taken about one or two fish off of hooks in my entire life. I prefer my fish to be beer battered with a whole bunch of tartar sauce right next to it. That's how I like my fish, all right? So understand that's where this is going to come from. So if you've got a fish and you've got on a fishing line, right? And you've got a 10-pound test line. What that means is that that line can hold about 10 pounds, right? So what happens is if you all of a sudden you get a 30-pound fish on there, what can take place is the weight of that fish, you try to pull that fish up, and its unbalanced force, meaning trying to go the opposite direction, could be enough where that tensionary force could actually cause that fishing line to snap. All right. Tubing behind a boat, you get the same thing. All of a sudden, they try to crack the whip on you, so you're going one way, they're going the other way, and all of a sudden that line stretches, and it pops and breaks. Right. That's what we kind of are looking at in tension. In a car, it could be a belt. All right. So, here we go. Tension. So we want to know what is the tension on a string. So if we have that 10 pound kilogram object, its weight is negative 98 newtons. Its tension should be 98 newtons. So if we're just holding it, what that means is that we are resisting the force of gravity, basically, right? So our tensionary force is positive because we're pulling that thing upwards at 98 newtons, right? Now, if we let it go, well, then its force is going to be, 98 newtons downwards towards the ground, right? So then we ask, if we accelerate it upwards at 3 meters per second squared, what is the tension? So now, what I want you to think about, when you lift up your backpacks, right? If you just hold them there, you're going to feel a certain amount of tension on that strap, on that, on that loop, right? Now, if you pull upwards on it or try and accelerate it and lift it fast, it feels heavier. Why? Because that's tension. That object wants to stay at rest. It doesn't want to move. That tension now starts to go up, 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 up. Now, because a lot of us carry huge amounts of weight in a backpack, eventually what happens is that tension breaks down the straps on our backpack, and they all of a sudden start to tear or something like that, right? So with this one, we want to know, does this cause a force? It should, right? Especially if it accelerates, right? So if it does cause a force, our fun equals ma, right? Our force equals the mass, this 10 kilograms up here. All right? This 10 kilograms here times what? Times the acceleration right there. All right? So fun equals ma, 10 times 3, it gets a 30 Newton force. All right? So then, knowing that, knowing that, we see our tension here on this thing should be 128 newtons. Should it be harder to lift an object up using a string or a rope or a cable or a wire? Yes, absolutely it should. Right? It's gonna take some force. Right? If you ever held up that prize-winning fish that you caught, right? It's gonna take some force sometimes to lift those big suckers up. All right, accelerating it downward. Now this one's weird. Okay. So what's gonna happen here is instead of just holding it, we're actually gonna try and throw it downwards. So we're gonna pull hard on this thing downwards. So does this cause a force? Well, if it's accelerating, it should cause a force, right? So then we say, all right, fun equals ma. Fun is the 10 kilograms times the -3. Now, why is it -3? Right? Again, it's -3 because we are going downwards there, right? So we get a -30 newtons of force. Well, why is that negative? Again, downward, right? So then what we see is we take that and we see it should have less tension, right? If it's just 98 by holding it here, we try to throw it down, we should be able to feel way less tension because that object wants to go that way anyway, if we were to let that rope go, all right? Try this one, all right? Give it a pause, try this one on. So you hang a 20 kilogram rock on a string, we want to know what is the tension on the string. If the rock is accelerated upwards at 2 meters per second, how much fun or unbalanced force did that acceleration take? What would the tension be? Okay, so give it a shot and try it out. There are your answers, okay? So question being, how do we get this 196? Well, the tension on the string, right? So that's going to be the upward pull on that string. That's going to be 20 times a -9.8. But if we look at the formula, T equals, and let me write that one out there, just to make your life easier. Color. All right. So if we say T equals MA minus mg, right? Our masses both here are going to be 20, right? So when we're just holding this strain in this first part here, what that means is that my acceleration in the first part is 0, but my gravity is still there at -9.8. So 20 times -9.8 is -196. But with that negative there, that makes it positive. We accelerate it upwards, right? Now, instead of this acceleration here being 0, now for this, so for the first part it was 0, right? For the second part, now it's 2, right? For this part, the gravity, still -9.8. That's not going to change for us, right? So we look at the first part. Well, what is the fun? Remember, this here in this equation, that's our fun. That's our unbalanced force, all right? So 20 times 2, that's where the 40 comes from. 40 plus the tension just on the rope, just holding it in place, is at 196. So 40 plus 196 gives us our 236. Okay? All right, last one. All right, check this out. All right, and this is where I'm going to leave you. Okay, if you feel like you can do this one and you can look at this one and get these answers and understand how these answers are conceived and made, great, awesome, perfect. Okay. Otherwise, that's kind of what I got for you today. So, take care, check this stuff out. I'll start getting homework out, later in the week here, more practice stuff like that, so that you got that. And I'll let you know quizzes and stuff like that. Okay. All right. Take care. Have a great day, folks. See you later.